everybody. Today, I'm going to be talking with Vanessa Kosoy. She is a research associate at the Machine Intelligence Research Institute, and she's worked for over 15 years in software engineering. About 7 years ago, she started AI alignment research and is now doing that full-time. Back in episode 5, she was on the show to talk about a sequence of posts introducing infra-Bayesianism. But today, we're going to be talking about her recent post, Infra-Bayesian Physicalism, a formal theory of naturalized induction, co-authored with Appel. For links to what we're discussing, you can check the description of this episode, and you can read the transcript at axrp.net. Vanessa, welcome to AXRP.
Thank you for inviting me.
Cool. So this episode is, I guess, about Infra-Bayesian Physicalism. Can you remind us of the basics of just what Infra-Bayesianism is?
Yes. So Infra-Bayesianism is a theory we came up with to solve the problem of non-realizability, which is how to do theoretical analysis of reinforcement learning algorithms in situations where you cannot assume that the environment is in your hypothesis class, which is something that has not been studied much in the literature for reinforcement learning specifically. And the way we approach this is by bringing in concepts from so-called imprecise probability theory, which is something that's mostly decision theorists and economists has been using. And the basic idea is instead of thinking of a probability distribution, you could be working with a convex set of probability distributions. That's what's called a cradle set in imprecise probability theory. And then when you're making decisions, instead of just maximizing the expected value of your utility function with respect to some probability distribution, you're maximizing the minimal expected value where you minimize over the set. So that's like as if you imagine an adversary is selecting some distribution out of the set. The nice thing about it is that you can start with this basic idea and, on the one hand, construct an entire theory analogous to classical probability theory. And then you can also use this to construct a theory of reinforcement learning and generalize various concepts like regret bounds that exist in classical reinforcement learning or like Markov decision processes. You can generalize all of those concepts to this imprecise setting.
Cool. So my understanding of the contributions, at least to what Infra-Bayesianism is, that you made, was basically that it was a way of combining imprecise probability with an update rule with like sequential decision making in some kind of coherent way. So like today, what I would want to do tomorrow if I learned that the sun was shining, once I wake up tomorrow, if the sun is actually shining, I still want to do that thing. Is that like roughly a good way of explaining what the contribution is, at least in those original posts?
Well, there are several aspects there. Like one aspect is the update rule. Here, I have to admit that an equivalent update rule has already been considered in a paper by Gilboa and Schmadler, but they described it as partial orders over policies. They did not describe it in the mathematical language which we used, which was of those convex sets of so-called A measures and the dual form where we use concave functionals on the space of functions. They did not have that. So we did contribute something to the update rule. And the other thing is combining all of this with concepts from reinforcement learning, such as regret bounds, and seeing that all of this makes sense, and the Markov decision processes, and so on. And the third thing was applying this to Newcombian kind of Newcomb paradox type situations to show that we are actually getting behavior that's more or less equivalent to so-called functional decision theory.
Cool. One kind of basic question I have about this. So last time we talked about this idea of like, every day you wake up and like there's some bit you get to see. It's 0 or 1, right? And you mentioned that like one thing you can do with infra-Bayesianism is you can have like some hypothesis about the even bits, but say like you don't know anything about the distribution of the odd bits or like how they relate to each other. And I was wondering if you could give us some sense of like we have this like convex probability distribution, maybe over the odd bits. What would we lose if we just averaged over that convex set? Like, what kind of behavior can we get with infra-Bayesianism that we couldn't get normally?
Well, there are several problems with this. Like one thing is that there's a technical problem that if your space is infinite dimensional, then it's very unclear what does it even mean to average over the convex set. But that's more of a technicality. The real problem is that any kind of average brings you basically back into the Bayesian setting. And in the Bayesian setting, you only have guarantees for environments that match something in your prior. So yeah, so only if you're like absolutely continuous with respect to your prior, then you can have some kind of guarantees. Or sometimes you can have some guarantees under some kind of an ergodicity assumption. But in general, it's very hard to guarantee anything. If if you're just have some arbitrary environment. Here we can have some guarantee. Like it's enough to for the environment to be somewhere inside the convex set that we can guarantee that the agent gets at least that much expected utility.
Okay, so putting that concretely, just to see if I understand, one sort of Bayesian thing I could do in the even and odd bits scenario is I could say that like on all the odd bits I have like I'm 50-50 on whether the bit will be 0 or 1, and it's independent and identically distributed on every odd day. Whereas like I could also have some sort of infra-Bayesian mixture or this set of like distributions that could happen on the odd days. And it seems like in terms of absolute continuity, one thing that could go wrong is it could be the case that actually like on the odd days 1/3 of the bits are 1 and 2/3 of the bits are 0, and that wouldn't be absolutely continuous with respect to my Bayesian prior, but it might still be in the convex set in the information setting. Am I understanding that correctly? Is that like a good example?
Yeah, like if your prior just does not have, like you can assume that the things you don't know are distributed uniformly, but in reality they are not distributed uniformly. They're distributed in some other way, and then you're just not going to like. What happens is that suppose you have several hypotheses about what is going on with the even bits, and one of them is correct. And with the odd bits, you don't have any hypothesis that matches what is correct. Then what happens with Bayesian updates is that you don't even converge to the correct things on the even bits. The fact that the odd bits are behaving in some way which is not captured by your prior causes you to fail to converge to correct beliefs about the even bits, even though the even bits are behaving in some regular way.
All right, cool. With that clarification, I've actually asked some people what they'd like me to ask in this interview, and I think a lot of people have the experience of maybe they're putting off reading these posts because they seem a bit mathy and they're not sure, like, maybe what they would get out of reading them. I was wondering if you could toot your own horn a little bit and say, like, what kind of insights might there be, or what can you say that might tempt people to really delve in and read about this?
Well, I think that infra-Bayesianism is important because it is at the center of a lot of important conceptual questions about AI and about AI alignment. Because in a lot of cases, like the inability to understand how to deal with non-realizability, it kind of causes challenges to naive attempts to come up with models of things. And Newcombian paradoxes is one example of that because like Newcombian paradoxes are inherently non-realizable, because you have this omega that simulates you, so you cannot be simulating omega.
Sure. And just in case people haven't heard of that, by Newcomian paradoxes, I guess you mean like situations where like you're making a decision, but some really smart agent has like figured out what you would do ahead of time and has changed your environment in ways that are maybe unknown to you by the time you're making the decision. Is that right?
Yeah, so Newcombian paradoxes means that your environment contains predictors which are able to predict your behavior either ahead of time or in some other counterfactual and do things that depend on that. And that's one type of situation where you have to somehow deal with non-realizability and and things like just averaging over the convex set, it just doesn't work. Another type of situation which is kind of related to that is multi-agent scenarios where you have several agents trying to make predictions about each other. And that's also something where it's not possible for all agents to be realizable with respect to each other, because that creates a sort of fluke paradox. And this, of course, has also implications for when you're thinking about agents that are trying to kind of self modify, or agents that are trying to construct smarter agents than themselves, all sorts of things like this. So, like, a lot of different questions you can ask kind of run up against problems that are caused by non-realizability, and you need to have some tool, some framework to deal with this.
Okay, cool. Moving on a bit, this post it claims to be some kind of theory of naturalized induction. Can you first tell me, like, what is naturalized induction?
Yes, so naturalized induction is a name invented by Miri, as far as I know, to the problem of how do you come up with a framework for AI in which you don't have this Cartesian boundary between the AI and its environment. Because, like, classical models, or you can call it like the classical cybernetic model, views AI as you have an agent and you have an environment, and they're completely separate, and the agent can take actions which influence the environment, and the agent can see observations, in which sense, like, the environment has some communication in the other direction, but there is some clear boundary between them, which is immutable. And this does not take into account a bunch of things. Things like the fact that the agent was created at some point and something existed before that. Things like that the agent might be destroyed at some point and something different will exist afterwards, or the agent can be modified, which you can use the special case of getting destroyed, but that's still something that you need to kind of contend with. And it also brings in the problem with the need to have those so-called bridge rules. So it's like, because you're working in this cybernetic framework, the hypotheses your agent constructs about the world are, they have to be phrased from the subjective point of view of the agent. So they cannot be phrased in terms of some kind of bird's eye view or whatever. And that means that the laws of physics are not a valid hypothesis. For to have a valid hypothesis, you need to have something like the laws of physics plus rules how to translate between the degrees of freedom that the laws of physics are described within to the actual observations of the agent. And that, like, makes the hypothesis much, much more complex, which creates a whole bunch of problems.
And why does it make it more complex?
So think about it as, like, we have Occam's razor, right, which is telling us that we should look for simple explanations, simple regularities in the world. And of course, Occam's razor is kind of the foundation of science and rational reasoning in general. But if you look at how physicists use Occam's razor, physicists, they say, okay, here, this is like, I don't know, quantum field theory or string theory or whatever. This is this really simple and elegant theory that explains everything. But the theory doesn't explain our observations directly, right? The theory is not phrased in terms of like what my eyes are going to see when I move my head like 2 degrees to the right or something. They're kind of described in terms of some fundamental degrees of freedom, quantum fields, particles, or whatever. And the translation between quantum fields and what my eye is going to see, or the camera of the eye is going to see, or whatever, that's something extremely complex. And like, it's not a simple and elegant equation. That's something monstrous. And people kind of have been trying to find frameworks to solve this. Well, at least people have been a little bit trying. So, like the classical framework for AI in the cybernetic, from the like cybernetic Cartesian point of view, is the so-called AIXI. So there have been some attempts. For example, Orson Ring had a paper called something like Space-Time Embedded Agents, where they kind of tried to extend this in some way which would account for those problems. But that did not really take off. Like there are problems with their solution and they haven't really followed up much on that. This is the crux of the problem I'm trying to solve here.
Okay. Can you give us a bit of a sense of why we should be excited for a solution to naturalized agency? Like, can we just sort of approximate it as some Cartesian thing and not worry too much?
Well, like I said, the fact that we need to add a whole bunch of complexity to our hypothesis, the fact that we need to add those bridge rules, it creates a range of problems. One problem is, first of all, this mere fact should make us suspicious that something has gone deeply wrong. Because if our starting point was Occam's razor, like that, we're assuming that simple hypothesis should be correct. And here, the hypothesis is not simple at all. So, like, why is our simplicity bias even going to work? And when we start analyzing it, we see that, yeah, we run into problems because what you can do thought experiments like what happens if you have an AI and someone throws a towel on the camera. So at this particular moment of time, all the pixels on the camera are black because the towel is blocking all the light. Now the eye can think and decide, what is the correct hypothesis is, this hypothesis, like I had this hypothesis before, but maybe the correct hypothesis is actually, if as long as not all the pixels are black, this is what happens, like ordinary physics. And at the moment all the pixels go black, something changes. I don't know, like the fine structure constant becomes different.
Yeah. And it could even become a simpler number.
Yeah. And from the perspective of like scientific reasoning, this sounds completely crazy hypothesis which should be discarded immediately. But from the perspective of a Cartesian AI system, this sounds very reasonable because it only increases the complexity by a very small amount. Because like this event of all the pixels becoming black, it's a natural event from a subjective point of view. It's like an event with very low description complexity. But from a point of view of physics, it's a very complex event. Like from the point of view of physics, when we are taking this kind of bird's eye view, we're saying, well, there's nothing special about this camera and about this towel. Like the fact that some camera somewhere has black pixels, that should not affect the fundamental laws of physics. Like that would be an extremely contrived modification of the laws of physics if that happened. So we should assign like extremely low probability to this. But the cybernetic agent does not assign low probability to this. So something is very weird about the way it's reasoning. And this is one example. Another example is thinking about evolution. Like the theory of evolution explains why we exist. Or like, we have theories about cosmology, which are also part of the explanation of why we exist. And those theories are kind of important in the way we reason about the world, and they help us understand all sorts of things about the world. But for the Cartesian agent, those questions don't make any sense because the Cartesian agent defines everything in terms of its subjective experiences. So things that happened before the agent existed or things that led to the agent to start existing, that's just nonsense. It's just not defined at all in the Cartesian framework. So those kinds of agents, they are just unable, kind of ontologically incapable of reasoning along those lines at all. And that seems like an indication that something is going wrong with them.
Okay. And I was wondering, so this problem of bridge rules first, can you give us a sense, like, informally, without going into the details, roughly, like, how is Infra-Bayesian Physicalism going to deal with this?
Yes. So the way we are going to deal with this is saying that we don't want our hypothesis to be describing the world from this subjective point of view, from the subjective perspective of the agent. We want our hypothesis to be describing the world from some kind of a quote unquote bird's eye view. And then the whole problem becomes okay, but how do you deal with the translation between the bird's eye view and the subjective view? Because the evidence that the agent actually has is the evidence of its senses. So it's evidence that exists in the subjective frame. And here, the key idea is that we find some mathematical way to make sense of the agent needs to look for itself inside the universe. So the agent has a hypothesis that kind of describes the universe from this bird's eye view. And then it says, I'm an agent with such and such source code that I know. And now I look into this universe and I'm searching for where inside this universe the source code is running. And if the source code is running in a particular place and receiving particular inputs, then those inputs are what I expect to see if I find myself in this universe. And this is how I measure my evidence against this kind of bird's eye view hypothesis.
Okay, cool. I also just want to go over. So there are some things that I guess I associate with the problem of naturalized agency, and I want to check like which ones of these do you think like infra-Bayesian physicalism is going to help me with. I guess the first thing on my list was world models that include the self, and it seems like yeah, this is naturalized infra-Bayesian physicalism is going to deal with this.
Yeah, that's true. So your world model is kind of describing the world. There's no longer a Cartesian boundary anywhere in there. So the world definitely contains you. Or, like, if the world does not contain you, then the agent's going to say, okay, this is a world where I don't exist, so I can safely ignore it, more or less.
Okay. The next one is sometimes people talk about logical uncertainty under this umbrella of naturalized induction. Are we going to understand that better?
So the way I look at it is that logical uncertainty is addressed to some extent by infra-Bayesianism, and then it's addressed even better if you're doing this thing which I've been calling Turing reinforcement learning, where you take an infra-Bayesian agent and say, okay, you also have some computer that you can play with that has a bunch of computational resources. And this is actually the starting point for physicalism. So when we go from this thing to physicalism, then I don't think it adds anything about logical uncertainty, qualogical uncertainty, but more about how do we use this notion of logical uncertainty that we're getting from infra-Bayesianism, or like infra-Bayesianism plus this Turing reinforcement learning thing. How do we use this notion of logical uncertainty and apply it to solve problems with naturalized induction? So it's definitely related.
Okay. Next thing on my list is open source game theory. So that's this idea that like I might be playing a game, but like you have my source code, so I don't just have to worry about like my actions. I have to worry about like what you will reason about my actions because you have my source code. Is information physicalism going to help me understand that?
So I don't think that that's a particularly, like, when I was thinking about this kind of multi-agent scenarios, I'm well, I don't really have a good solution yet, but I'm imagining that some kind of solution can come from just looking at some more classical kind of Cartesian setting. It doesn't feel like the physicalism part is really necessary here, because you can just kind of imagine having several Cartesian agents that are kind of interacting with each other, and that's probably gonna be fine. So I'm not sure that the physicalism part actually adds something important to thinking about this.
Yeah, it actually makes me wonder. So, just from the informal thing you said, there's this idea that like I have this world model and I look in it for my program being executed somewhere. In the open source game theory setting, it seems like my program's being executed in two places. Maybe it's not being executed, but it's being reasoned about somehow. Like, is there a way of picking that up?
Yeah, so there is certainly some relation in this regard. but I'm still not sure that it's very important because, like, in some sense, you already get that in infra-Bayesianism, right? Like, with infra-Bayesianism, we can deal with those kind of new Combian situations where, like, outside world contains predictors of me, and that's kind of a very similar type of thing. So it feels like going to physicalist mostly buys you something which kind of looks like having, it's not exactly having a better prior, but it's kind of similar to having a better prior, more than, like, if you can kind of formalize your situation by, like, I already have a good enough prior that, let's just assume I have this prior which contains all the hypotheses I need and go from there, then it doesn't seem like you really need physicalism at this stage. And it seems like, at least for the initial investigation, understanding open source game theory should be possible with this kind of approach without invoking physicalism, as far as I can tell. I mean, you do want to do physicalism if you are considering more specific examples of it, like a causal bargaining. You're thinking of a causal bargaining with agents that exist in some other universes or weird things like that.
Sorry, what is acausal bargaining?
So, a causal bargaining is the idea that if you have two agents that do not have any causal access to each other, so they might be just really far from each other, or they might be literally in different universes, they don't have any physical communication channels with each other, they might still do some kind of cooperation. Because those agents can kind of imagine the other universe and imagine the agent in the other universe, and by kind of having this sort of thinking where each of them can kind of reason abstractly about the other, they might strike deals. For example, I like apples, but there's another agent which likes bananas. But my universe in which I live is not super good for growing apples, but it's really good for growing bananas. But the other universe, the agent that likes apples believes, the other universe, it has like the opposite property. So we could both benefit if we start growing the fruit that the other agent likes in our own universe. Assuming that our utility function kind of considers that having bananas or apples in a different universe to be an actual game. So this is like an example of a causal bargaining. And when you're stacking, so this is in some sense a special case of open source game theory, but here it becomes kind of more important to understand, how do you even reason about, how does agents reason about this? How do they know that this other agent exists? What kind of weight they assign to those other universes or whatever. And when you go to this kind of questions, then physicalism definitely becomes important.
Okay. So the next thing on my list is logical counterfactuals. So sometimes people say that it's like important to be able to do counterfactuals where you're like, okay, this like logical statement that I've proved already, what if it were false? What if like I've reasons about this program and I know that it would do this thing, but what if it did this other thing instead? Is information physicalism going to help me with that?
Yeah, so what's happening here is, I mean, here my answer would be similar to the question about logical uncertainty. That in some sense, infra-Bayesianism already gives you some notion of logical counterfactuals, and this is what we're using here. Like, we're using this notion of logical counterfactuals. There is some nuance here because to get physicalism work correctly, we need to be careful about how we define these counterfactuals, and this is something we talk about in the article. But like the core, like mathematical technique here is just using this fact in information, because like the basic idea is that in informationism you can have this kind of Knightian uncertainty, and what we're doing here is saying, like, assume you have Knightian uncertainty about the outcome of a computation, then you can build counterfactuals by forming those sort of logical conjunctions, which, you can, like, information is, you can kind of define conjunctions of beliefs. So once you have like Knightian uncertainty about whether this computation is going to be 0 or 1. You can take the conjunction with, assume this computation is 0 and see what comes out from it. And in some sense, you can say that infra-Bayesian agents, the way they make decisions is by the same kind of counterfactual, is by kind of forming the conjunction with, like, what if I take this action?
Okay, cool. And 99 uncertainty, am I right that that's just like when you don't know what probability distribution you should assign? And so maybe you use a convex set or something.
Yeah. Naive uncertainty is like when you, instead of having the single probability, you have like in your convex set, you have probability distributions which assign different probabilities to this event.
Okay. And the last thing I wanted to ask about is self improvement. So sometimes people say, like, yeah, this problem of what would happen if I modified myself to be smarter or something. People sometimes lump this under the umbrella of naturalized induction. Will infra-Bayesian physicalism help me with this?
Yeah, so I mean, here also I feel like the initial investigation of this question, at the very least, can be done just with Turing reinforcement theory. Because, like, if you're already able to have non-realizability and you can kind of reason about computations, then you can also reason about what happens if I like build a new agent and this agent might be smarter than me and so forth. These sort of questions are kind of already covered by infra-Bayesianism plus Turing reinforcement theory in some sense. The physicalism part helps you when you get into trouble with questions that have to do with the prior. Questions like anthropic reasoning or acausal interactions between agents in different universes, and of course, like the bridge rules themselves, and so on and so forth. Questions where you can kind of imagine some kind of a simplistic synthetic toy model environment where you're doing things, which is kind of in kind of abstract a way dealing with actual physics and anything related to actual physics. Those are questions for which you don't really need physicalism, at least on the level of solving them for some basic toy setting.
Okay, great. Now that we've heard what information physicalism is roughly supposed to do, let's move on a bit to how it works. So the first thing I want to talk about is the world models used in information physicalism. Can you give me some, more technical detail on like what's the structure of these world models that we're going to be using?
Yeah, so the world model is a belief about, we're considering joint beliefs about physics and about computations. So, what does that mean? So, physics is just, there is some physical universe, so there is some kind of a state space, or, should think of it as a timeless state space. Like, what are all the possible histories? What are, like, all the possible ways the universe can be across time and space and whatever. So there is some space which we define, which is like the space of all things the universe can be. And this space, it can depend on the hypothesis. So it can be anything. Like each hypothesis is allowed to postulate its own space of physical states. And then the other part is the computations. So that's what we denote by gamma. And this gamma is mappings from programs to outputs. So we can imagine something like, the set of all Turing machines, or like the set of all programs for some universal Turing machine, which we assume to be, let's assume that every Turing machine outputs a bit, like 0 or 1. So mappings from the set to the set 0, 1, we can think of it as like the set of computational universes, like the set of ways that the universe can be in terms of like just abstract computations and not physics.
Okay, so this would include something like there's some universe where like when I run a program to check if the Riemann hypothesis is true, right? In some like computational universe, that program outputs like yes, it is true. In some computational universe, it outputs no, it's not true. Is that how I should sort of understand it?
Yeah, this is about right, except that, of course, in the specific case of the Riemann hypothesis, you don't really have we don't have a single Turing machine that you can run and it will tell you this. You can only check it for like every finite approximation or something.
Okay. I actually wanted to ask about that because in the real world there are some programs that like don't output anything. They just like continue running. And I don't necessarily know which programs those are. So do I also get to have uncertainty over which programs do actually output anything?
Yeah, you don't necessarily know, and in fact, you necessarily don't know, like because of the healthy problem, right? But yeah, this is a good question, and we initially thought about this, but then at some stage, I just realized that you don't actually need to worry about this because, like, you can just have your computational universe to assign an output to every program, and some programs in reality are not going to halt and not going to produce any output, but you just don't care about this. So like if a program doesn't halt, it just means that you're never gonna have empirical evidence about whether its output is 0 or 1. So you're always gonna like remain uncertain about this. But it doesn't matter really. Like you can just imagine that it has some output and in reality it doesn't have any output, but since you don't know what the output is anyway, it doesn't really bother you.
Okay. So it's sort of like our models are containing this like extra fact about these programs. Like we're imagining, like, yeah, maybe once it runs for infinite time, is it going to output 0 or 1? Like,
Hmm.
seems like I'm entertaining the possibility. Okay. So we have these models that's the computational universe and it's also the state space, right?
Yeah, and then like your hypothesis is a joint belief about both of them. So it means that it's an infra distribution over the product phi times gamma. And we use some specific type of infra distributions in the post, which we call, well, actually for technical reasons, we call them ultra distributions in this post. But this is just an equivalent way of looking at the same thing. So just instead of infra distributions and utility functions, we use ultra distributions and loss functions. But that's just like a different notation, which happens to be more convenient.
Okay. And infra distributions are just these convex sets, right, of distributions.
Well, yeah, like what we call crisp infradistribution is just a convex set of distribution.
Okay.
A general infradistribution is something slightly more general than that. Like it can be a convex set of those so-called A measures, or it can be described as a concave functional over the space of functions. So it's something somewhat more general. And specifically in this post, we consider so-called homogeneous ultra distributions, which is like a specific type. And this is something that you can think about as like instead of having convex set of distributions, you have a convex set of what we call contributions, which are measures that can sum up to less than one. So like the total mass is less or equal to one. And the set has to be closed under taking a smaller contribution. Like if you have a contribution, you take one which is just lower everywhere, then it also has to be in the set. And like those kinds of objects, we call them homogeneous ultra distributions. And like your usual kind of vanilla set of distribution, convex set of intradistributions is a special case of this.
Okay. You said we had this set of ultra distribution over phi times gamma. Gamma was the computational universe. And what's phi?
And phi is the space of states of the physical universe. States or histories, maybe even more kind of timeless states or histories.
Okay. So that's the model we're using. Can you give me a sense of like, so it seems like we're sort of putting this prior over, over what computations might have what outputs. Do you have a sense of like what kind of prior I might want to use and whether I might want it to be entangled with the physical world? Because like, it seems like that's allowed.
Yeah, you absolutely super want it to be entangled because otherwise it's just not going to work. Like the sort of prior that you want to use here is a simplicity prior because like that's in some sense the whole point is having Occam's razor. So we haven't actually defined explicitly simplicity prior in the setting in the article. But it's not difficult to imagine ways in which you could define it. For example, there's something that I have in an old post of mine where you can construct this kind of prior over, this kind of convex sets by taking like the Solomonov prior construction and instead of Turing machines, taking Oracle machines. And then like the Oracle is kind of the source of night and uncertainty. So it's not hard to construct something analogous to the Solomon of prior for this type of hypothesis. And this is what you should be using in some sense.
All right. Yeah, when you say they should be entangled, I guess that's because like a universe where like I physically type in some program and my physical actual computer outputs something, like that should tell me about the computational universe, right?
Yeah, like the fact the formalism works is like the entanglement is what tells you which computations are actually running. So it's like
Okay.
yeah, exactly. Like if you're running some computation on your computer and you don't know what the result is going to be, then you have some uncertainty about the computation and you have some uncertainty about the number which will appear on the screen, which is like some property of the physical universe. And the two are entangled together, right? You know that whatever number appears on the screen is the actual output of this computation.
Okay. And how much work do I have to do to specify that entanglement? Like, does that come in some sense for free, or when I'm like defining my models, do I need to like carefully say like which like physical situations count as which computer programs?
Well, you start with a prior, which is by default it's like a non-informative prior, right? So it's something like Solomonov prior. So anything goes. Like maybe we have this entanglement, maybe we have that entanglement, maybe we have no entanglement, maybe we have whatever. Like the important thing is that the agent is able to use the empirical evidence it has in order to start narrowing things down or like updating away from this prior in some sense. Like updating away in some sense because the formalism is actually updateless. It just like decides on some policy in advance. But like in practice, like the things you do when you see particular things, like on a particular branch of on the tree of things that could happen, would be dictated by some kind of subset of hypotheses which seem more likely on this tree in some sense.
Okay. And I guess that's how I'm like learning about like which computations are being implemented if I'm thinking of the updateful version. And you mentioned that we were going to have counterfactuals earlier. Can you say a little bit more about like what exactly counterfactuals about computations are going to look like here?
Well, the basic idea is kind of simple. Like the basic idea is if there's a particular computation, then we can consider we have some belief about computations or belief about universe times computation. And then there's a particular computation, and we want to consider the counterfactual that its output is zero. Then all we need to do is take a subset. So we had this convex set of distributions, or more precisely, convex set of contributions. And now all we need to do is take the subset of the contributions which assign probability zero to the other thing, which is like not supposed to happen. And that's our counterfactual. And like that's the basic building block here.
Cool. All right. So yeah, when we're talking a bit more specifically about how the self is fitting in, is the idea that like I've got this physical world model and like somehow I'm looking for parts which give evidence about the results of my computation, or yeah, what's actually going on when I'm like trying to locate myself in a world model in this setting?
Yeah, so the key mathematical object here is something that we call the bridge transform. That's actually what enables you to kind of locate yourself inside this hypothesis or inside the universe described by this hypothesis. And the idea here is that the bridge transform is a formal way of looking at this hypothesis and exploiting the entanglement between the computational part and the physical part in order to say which computations are actually running in the physical universe and which computations are not running. So more precisely, the more precise way to think about it is there are some facts about the computational universe that the physics knows, that the physics kind of encodes or knows or whatever you like to call it. And you can describe this as some subset of gamma, like as some element of 2 to the gamma or subset of gamma. Like the subset of gamma of like things that the universe knows that the physical universe knows that the computational universe is somewhere inside this subset. And then what the bridge transform does, it starts with our hypothesis about phi times gamma and transforms it to a hypothesis about phi times 2 to the gamma times gamma.
Okay. And how does it do that?
Yeah, so the idea here is this connects again to the question of counterfactuals, because in some sense, what does it mean for the universe to be running a particular computation? The answer we give here is phrased in informal terms is the universe runs a computation when the two counterfactuals corresponding, or like the counterfactuals corresponding to the different outputs of this computation look differently in the physical world. So if I consider the counterfactual in which a certain program outputs 0 versus the computation in which a certain program outputs 1, and I look how the physical universe looks like in those two counterfactuals. If the universe looks like the same, then it means that it's not actually running this program, or at least we cannot be sure that it's running this program. Whereas if they look completely differently, like two distributions with disjoint supports, for example, then we're sure that the universe is running this program. And there can also be an intermediate situation in which you have like two distributions and they're kind of overlapping. And then the size of the overlap determines the probability with which the universe is running this program.
Okay. So that's the bridge transformation. And so basically we're saying like, does the universe look different depending on how we say what the output of this program is? And it tells us like which programs the universe is running. How does that help us locate the self?
Yeah, the way it helps us locate the self is by using your own source code. Like, if you're an agent and you know your own source code, and we know that at least in like computer science world, that's not hard to know your source code because you can always use quieting to kind of access your own source code in some sense. Then you can ask, okay, my source code. So what does it mean? Your source code. Your source code is it's like a program that gets the history of your past observations and actions as input and produces a new action as output. So this thing, if the universe is running it with a particular input, then it means that I exist in the universe and I observe this input, right? So and like conversely, if I'm an agent and I know that I have seen a certain input, then this allows me to say that, okay, this is information about the true hypothesis. We know that the true hypothesis has the property that the universe is running the program, which is me, with this input.
Okay. So this basically means that the equivalent of bridge rules is just that like I'm checking if like my hypothesis about the universe would it look any different depending on what I am or like what actions I would produce in response to given observations. Is that roughly right?
Yeah, it means that, like, if suppose that, like I'm looking at a hypothesis and I want to know that is this hypothesis predicting that I'm going to see a red room? So I'm thinking, okay, suppose there's the program which is me, which is getting an input which is the red room, and it has an output which says should I lift my right hand or should I lift my left hand? And now I consider two counterfactuals. The counterfactual in which upon seeing the red room I decide to lift my left hand, and the counterfactual in which upon seeing the red room I decide to lift my right hand. And those are kind of two computational counterfactuals, because I'm just thinking about this in terms of computation. There's the computation, which is me receiving the input, which is the red room, and producing the output, which is which arm to lift. So if in those two counterfactuals, the hypothesis says that the physical universe looks different, then this is equivalent to saying this hypothesis is actually predicting that I'm going to see a red room, because this hypothesis says that the universe is running the program, which is me, with an input, which is a red room.
Okay, so this is reminding me a bit of Anthropics. In particular, in Anthropics, people sometimes wonder like how you should reason about different universes that might have more or fewer copies of yourself. So like if I learned that like there's one universe where there's like only one person just like me versus another universe where there are 10 people like me, some people think like I should consider those just as likely, where some people think like, well, the one where there are 10 times as many me's, I should think that I'm like 10 times as likely to be in that one. It sounds like if you're just considering does the universe look different depending on the outputs of my actions, it sounds like you're sort of equally weighting universes in which there's like just one of me versus universes where there's 10 of me, or like it seems like it's hard to distinguish those. Is that fair to say?
Yeah, it's absolutely fair. So definitely the theory of anthropics that IB physicalist agents have is a theory in which the number of copies doesn't matter. It doesn't matter if the universe is running one copy of you with a certain input or 80 copies. That's not even a well-defined thing. And it's not so surprising that it's not a well-defined thing, because if you believe that it should be a well-defined thing, then you quickly run into philosophical conundrums like, okay, if I'm just using a computer with thicker wires or whatever to run the same computation, does it count as having more copies of the AI or whatever? And the physicalist answer is there's no such thing as number of copies. There's like either I exist or I don't exist, or maybe the hypothesis thinks I exist with some probabilities, but I mean, there might be different copies in the sense that different branches, right? Like there is me now observing something, and then there are different things I can observe in the future, and there are hypotheses which are going to predict that you will observe both. Like I'm about to enter a room, and the room is going to be either green or red, and some hypotheses are going to say, well, the universe is running you with both inputs, both with the input red room and the input green room. So like in this sense, there are two copies of you in the universe seeing different things. But each branch, like given a particular history of observations, there's no notion of number of copies that see this history.
Okay, so you mentioned that like you should be suspicious of the number of copies of things because this argument involving computers with thick wires. Can you spell that out? Why do thick wires pose a problem for this view?
Yeah, I mean, like think of an AI. So what does it mean? So an AI is a program running a computer. So what does it mean to have several copies? So we can imagine like having some computer, like a server standing somewhere, and then like there's another server in another room, and we think of it as two copies. Okay, suppose that's two copies, but now let's say that the two servers are standing in the same room next to each other. Is this still two copies? Okay, suppose it is. Now let's suppose that instead this is just like a single computer, but for purposes of redundancy, every byte that it's computed is computed twice to like account for random errors from cosmic rays or whatever. Does this still count as two copies? At some point it's getting really not clear where the boundary is between different copies and just the same thing. And it's really unclear how to define it in general case.
Okay, so getting back to information physicalism. So we had these world models where, like, you had this uncertainty over the computational universe and the physical universe, and you also have this bridge transform, which lets you know, like, what computations are being run in a given universe, and you can check if, like, your computation is being run in some universe. Next, what I want to ask about is how you have loss functions. Because if I'm being an agent, I need models and I also need like some kind of utility function or a loss function or something. Can you tell me what those will look like in the Infra-Bayesian physicalist setting?
Yeah, so this is another interesting question because In the cybernetic framework, the loss function is just a function of your observations and actions. And that in itself is another thing about the cybernetic framework, which is kind of problematic because in the real world, we kind of expect agents to be able to care or, assign some importance to things that they don't necessarily observe directly, right? Like, yeah, so we can easily imagine agents caring about things that they don't directly observe. Like, I care about some person suffering even though I don't see the person. Or a paperclip maximizer wants to make a lot of paperclips even if it doesn't see the paperclips all the time. So one problem with the cybernetic framework is that you can only assign rewards or losses or whatever to things that you observe. In the physicalist framework, it's very different. In the physicalist framework, your loss function is a function of gamma times 2 to the gamma. In other words, your loss function is a function of which computations are running, roughly speaking, and what are the outputs of these computations. And this kind of can encode all sorts of things in the world, right? Like if there's some computation in the world which is a person suffering, then I can care about the universe running this computation, for example.
Okay. And basically that gets encoded in yeah, 2 to the gamma tells me which computations are running in the world, and I can care about having fewer computations like that or more computations like that.
Yeah, only there is a huge caveat, and the huge caveat is what we call the monotonicity principle. So monotonicity principle is like the weirdest and most kind of controversial and unclear thing about the whole framework, because the monotonicity principle basically says that your loss function has to be monotonic in which programs are running. So physicalist agents, the way we define them, they can always only be happier if more programs are running and more kind of upset if less programs are running. They can never have the opposite behavior. And that's kind of a weird constraint which we have all sorts of speculations about how to think about it, but I don't think we have a really good understanding of how to think about it.
Huh. Yeah. So it sounds like that means that I can't if there's some program that's a happy dude, living a fun life, and if there's some program that's an unfortunate person whose wishes they don't exist. So the monotonicity principle is saying I either prefer both of them happening, or I disprefer both of them happening, but I can't like one happening but dislike the other happening.
Yeah, you cannot have a preference which says this program I specific is like a bad program which I don't want to run. Like this is something that's not really allowed.
Huh. And why do we have that principle in infra-Bayesianism? Why can't you just allow any loss function?
So the reason you have this is because the bridge transform produces ultra distributions which are downwards closed, meaning that so in simple words, what it means is that you can never be sure that some program is not running. Like you can be certain that some program is running, but you always have instead of being certain about the fact that some program is not running, the closest thing you can have is just 19 uncertainty about whether it's running or not. It's always possible that it is running. So given this situation, it's not meaningful to try to prefer for a program not to run because it always might be running, and because you resolve your 19 uncertainty by you always by checking the worst case. The worst case is always gonna be okay, if you prefer this program not to run, the worst case is always that it runs, and then there's nothing you can do about it. And the reason you cannot be certain that the program is not running, well, I mean the reason is that's just how the bridge transform works, but in some sense it's a consequence of the fact that you can always have refinements of your state space. Like the state space phi, which we discussed before, we say that it kind of the space of all the ways the universe can be. but describe in what terms, right? We can kind of describe the ways the universe can be in terms of tennis balls, in terms of people, or in terms of like bacteria or something, I don't know, or in terms of atoms, or in terms of quantum fields. Like you can have different levels of granularity. And the kind of nice thing is that we have a natural notion of refinement. Like given a hypothesis, we can consider various refinements, which are like higher granularity descriptions of the universe, which are consistent with the hypothesis that we have on this coarse level. And the agent is kind of, you should think of it as kind of always trying to find refinements of the hypothesis it has in order to use this refinement to have less losses or like more utility. And the thing is that this process is like not bounded by anything. Like the agent always thinks that like it has an ideal uncertainty. As far as it knows, the description of the universe it has, it might be just a coarse grained description of something other, more refined, which is happening in the background. And because you can always have more and more refinements, like you cannot ever have any level of certainty that there is no longer any refinement, you can always have more programs running because maybe the more refined description has additional programs running that the more coarse grained description does not capture. It's like, maybe the description we have in terms of quantum fields, maybe there are some sub quantum field thingies which we don't know about that encode lots of suffering humans, and like we don't know. That is how you think if you're an IB physicalist.
Okay, so that does seem counterintuitive. Let's put that aside for the moment. So you said that the loss function was just in terms of which computational universe you're actually in and what you know about the computational universe, like which element of gamma and which element of 2 to the gamma. So there's some intuition that it makes sense to want things about the physical state. Like in fact, earlier you said like you might want to have a utility function that like just values like creating paper clips, even if you don't know about the paper clips. So yeah, how do I phrase that in this setting?
Yeah, so this is an interesting question, and you could try to have loss functions that care directly about the physical state, but that quickly runs into the same problems that you were trying to solve, because then you end up again requiring to have some bridge rules as part of your hypothesis, because the things you care about are not the quarks. The things you care about are some complex macroscopic thingies, and then like you end up requiring your hypothesis to have some bridge rules that would explain how to produce this microscopic thingies, and this kind of creates all the problems you were trying to avoid. So the kind of radical answer that physicalist agents have, or like at least kind of purist physicalist agents, they say, no, we're just going to be computationalist. We do not care directly about physical things. We only care about computations. So if you want to be a physicalist paperclip maximizer, then what you need to do in this case is have some model of physics in which it's possible to define the notion of paperclips and say the computations that I care about are the computation comprising this model of physics. And then it's like I want computations, like if there's a computations that's simulating a physical universe that has a lot of paper clips in it, that's the computation that I want to be running. Like that's what it means to be a paperclip maximizer if you're a physicalist.
Okay, cool. And what would it look like to have a selfish loss function where I'm just like, I want to be a certain way or I want to be happy or something?
Yeah, so if you're doing a selfish loss function, then the computations you're looking at are your own source code, right? Like we had this thing before, which we used to define this counterfactuals, which is like your own source code. So you're checking where the universe is running your source codes with particular inputs. It is also something that you can use to build your loss function. You can say your loss function is I want the universe to run the source code, which is me, with an input that says, I'm taking a nice bath and eating some really tasty food or whatever.
Okay. All right, cool. And pro social loss functions would be something like me having a loss function that says I want there to be lots of programs that simulate like various people, you know, what they would do if they were in a nice bath and eating tasty food. Is that roughly right?
Yeah, you can think of like programs which represent other people, or you can think about something like a program which represents society as a whole. Like you can think of society also as a certain computation where like you have different people and you have like the interactions between those people. Like all of this thing is some kind of a computation which is going on. So, you know, I want the universe to be running this kind of computation with some particular thingies which make me like this kind of society and not the other kind of society or whatever.
Okay, cool. So another question I have is, so one preference that it seems like you might want to express is if physics is this way, I want this type of thing, but if physics works some different way, then I don't want that anymore. So like you could imagine thinking like, look, if classical physics exists, then I really care about there being like certain types of particles in certain arrangements. But like if quantum physics exists, then like I realize that I don't actually care about those. I only cared about them because I thought they were made about particles. And so like maybe in the classical universe I cared about particles comprising the shapes of chairs, but in the quantum universe, like then, you know, what I want is like I want there to be sofas, but I don't want there to be chairs because like sofas fit the quantum universe better. Can I have preferences like that?
Yeah, so in some sense you cannot. Like if you're going with infra-Bayesian physicalism, that you're kind of you're committing to computationalism. So committing to computationalism means that there is no difference between a thing and a simulation of the thing. So this is actually a pipe. Like if there's like some type of physical thing that you really want to exist, or someone is just running a simulation of this physical thing, from your perspective, that's equally valuable. And this is like an interesting philosophical thing which you can find objectionable, or on the contrary, you can find it kind of liberating in the sense that it kind of absolves you from all the philosophical conundrums that come up with what is even the difference between something running in a simulation and not in a simulation. You know, like maybe we are all a simulation that's running inside quantum strings in some sense, but does it mean that we are not real? Like does it really matter whether the universe is made of strings or quarks in the fundamental level of something else? Like, should it change, you know, the extent to which I like trees and happy people and whatever the thing I like is? So if you're a computationalist, then you say that I don't care. I don't know what's the basic substrate of the universe. I just care about the computation.
Yeah. It seems weird because it seems even hard to distinguish like I might have thought that I could distinguish like here's one universe that actually runs on quantum mechanics, but like it simulates a classical mechanical universe, right? That's world A. In world B, it actually runs on classical mechanics, but there's a classical computer that simulates like the quantum world. And it seems like in infra-Bayesian physicalism, like my loss function can't really distinguish world A from world B. Is that right?
Yeah, that's about right. So you care about which computations are running, or maybe what outputs they have, but like you don't care about the physical implementation of these computations at all.
Okay, gotcha. And so to wrap that up together, so we have these world models and we have these loss functions. Can you just reiterate like how you make decisions given these world models and these loss functions?
Yeah, so the way you make decisions is by applying counterfactuals corresponding to different policies, right? So like you're kind of considering what if I follow this policy, what if I follow that policy, and now you're supposed to somehow compute what's your expected loss is going to be and choose the policy which has the minimal expected loss. So the way you actually do it is you construct counterfactuals corresponding to different policies. And the way you construct those counterfactuals is, well, to first approximation, they're just the same kind of logical or computational counterfactual we had before. So they're just saying, suppose that the computation, which is me, is producing outputs which are consistent with this policy, and let's apply this counterfactual the way we always do it, to our hypothesis or prior, and let's evaluate the expected loss from that thing. But the thing that you actually need to do is slightly more tricky than that, because if you do this naively, then you run into problems where you're never gonna be able to learn. Like you're never gonna be able to have good learning theoretic guarantees. Because the problem with this is that if you're doing this way, then it means that you cannot rely on your memory to be true. You wake up with certain memories, but you don't know whether these memories are things that actually happened, or maybe it's just someone simulating you already having these memories. And because you don't know whether these things actually happened, you cannot really update on them, and you cannot really learn anything with certainty. But we can fix this by changing our definition of counterfactuals. And the way we change the definition is kind of informally what it means is we don't take responsibility about the output of my own computation if it's not continuous. Like if there is some continuous sequence of like memories which is leading to a certain state, to a certain mental state, then I take responsibility of what I'm going to do in this mental state. But if something is discontinuous, if like someone is just simulating me waking up with some weird memories, then I don't take responsibility for what that weird simulation of me is going to do. I don't use that in my loss calculus at all. I just consider this as something external and not under my control.
Okay. And formally, what does that definition look like?
Well, more formally, it looks like what happens is to each policy you correspond some subset of 2 to the gamma times gamma. Like the subset of things which are consistent with this policy. And in the naive version, that would be just let's look at the computational universe gamma, and let's look at the source code which is me, and see that it outputs something consistent with the policy. In the more sophisticated version, we're looking like, okay, let's also look at 2 to the gamma and see with which inputs the universe is actually running me. And then we're only going to apply our constraints to those inputs which have a continuous history. And like that's one thing we need to do. And the other thing is need to do related to this envelope. We haven't really discussed it before, but there's like an important part where you're doing this kind of Turing reinforcement learning thing. Like your agent has some external computer that it can use to do computational experiments, like run all sorts of programs and see what happens. And there, you also need a corresponding guarantee that your computer is actually working correctly, right? Because, like, if your computer has bugs and it's just returning wrong things, then you cannot really update on seeing what it returns. So it creates again problems with learning. And like in order to not to have that thing, you need to apply a similar fix where you kind of only apply the constraint of like your source code's outputs are consistent with the policy on branches of the history in which you have only seen the computer saying true things.
Okay. So I can sort of see how you would operationalize you only see the computer saying true things. But what does it look like to operationalize like there's this continuous history of your program existing? Like if I go to sleep or go under general anesthesia, is that going to invalidate this condition?
That depends on your underlying model. It assumes that in our formalism, we just have like the inputs to our source code, to our agent, are just a sequence of actions and observations. So, like, if you go to sleep with like some sequence of actions and observations, and you wake up and the actions and observations continue from the same point, right? Like the things in between, they're just not contributing to the sequence. That's continuous as far as you're concerned. So, like, the continuity is not physical continuity, but it's more like logical continuity. The continuity means that, like, someone runs your code with certain observation, then someone runs your code with certain observation. The action that you outputted on the previous observation. That's also important, by the way. Like, you're not allowed to, like, another type of thing which is kind of not allowed is someone running you on memories of you doing something which you wouldn't actually do. That's also something which we kind of exclude. So then we have like observation, action leading from this observation in another observation. And then you have like a sequence with 3 observations, 5, 7, and so on. So those form kind of a continuous sequence. So this is continuity. Like, if you have some sequence on which someone is running you, but there is some prefix of the sequence on which the universe is not running you, then that's considered not continuous.
Okay. And the point of this was so that you could prove like loss bounds or something on agents. What loss bounds are you actually able to get in this setting?
Well, we haven't actually proved any loss bounds in this article, but the idea showed that you kind of can prove at least some very simplistic loss bounds along the lines of, like, okay, let's assume there is some experiment you can do which can tell you in which universe you are, or like some experiment which you can do which can at least distinguish between some classes of universes in which you might be. And let's further assume that this experiment in itself doesn't carry any loss, or like almost any loss. So just committing to this experiment doesn't cost you anything. Then, in this situation, the loss the agent would get would be as if it already knows in which universe or in which class universes it exists from the start. Or like a similar thing which you can do with computational thing is like, assume that you can like run some computation on your computer, and the fact of running it in itself doesn't cost you anything. Then you can kind of get a loss bound which corresponds to already knowing the result of this computation.
Okay. And that actually relates to another question that I wanted to ask, which is like if you imagine implementing an agent in the infra-Bayesian setting, like how tractable can you actually compute the outputs of this agent? Or is this going to be something like IC, where it's theoretically nice, but you can't actually ever compute it?
Well, that's definitely going to depend on your prior, which is like the same thing as with classical reinforcement learning. So, like with classical reinforcement learning, if your prior is the Solomon of prior, you get AXI, which is uncomputable. But if your prior is something else, then you get something computable. Like, you can take your prior to be some kind of a bounded Solomon of prior, and then like the result is computable, but like still very, very expensive. Or you can take your prior to be something really simple, like all MDPs with some number of states, and then like the result is just like the Bayes option. The result is computable in like polynomial times number of states, whatever. So the same kind of game is going on with infra-Bayesianism. Depending on what prior you come up with, you can have different levels of the computation complexity of computing the optimal policy, or like approximating the optimal policy, is going to be different. And we don't have like a super detailed theory which already tells us what is happening in every case. But even in classical reinforcement learning without information, we have large gaps in our knowledge of like which exactly priors are efficiently computable in this sense, not to mention in the information case. So I have some extremely preliminary results where you can do things like have information versions of Markov decision processes, and under some assumptions you can have like policies which are seem to be about as hard to compute as in the classical case or something. But there is actually some paper which is not by me, which just talks about kind of zero sum games, kind of reinforcement learning where you're kind of playing a zero sum game, but that actually can be shown to be equivalent to a certain information thingy. And yeah, they prove some kind of regret bound with, I think, an efficient algorithm. Actually, not 100% sure, but I think they have a computationally efficient algorithm there. So, at least in some cases, you can have a computationally efficient algorithm for this thing. But the general question is very much open.
All right. So, getting more to questions about extensions and follow-ups. What follow-up work to, I guess, either infra-Bayesianism in general or infra-Bayesian physicalism in particular are you most excited about?
Yeah, so there's a lot of interesting directions that I want to pursue with this work at some point. One direction which is really interesting is solving the interpretation of quantum mechanics. So that's like something which, well, I mean, quantum mechanics, you can say, why do we even care about this? You know, who cares about quantum mechanics? AI is going to kill us all. So I think that's interesting in the sense that it's a very interesting test case. Like the fact that we're so confused on the philosophical level about quantum mechanics seems to be an indication of our insufficiently good understanding of kind of metaphysics or epistemology or whatever. And it seems to be kind of pretty related to this questions of naturalized induction, which we have been talking about. So, if information physicalism is a good solution to naturalized induction, then we should expect it to produce a good solution to all the confusion of quantum mechanics. And here I have some fascinating but very preliminary work which shows that I think it can solve the confusion. Specifically, I have some concrete mathematical way in which I can build an information hypothesis that corresponds to quantum mechanics. And I think that I can prove, well, I kind of sketched it. I haven't really written it in enough detail to be completely confident, except for some simple special cases. But I believe that I can prove that with this construction, the bridge transform reproduces all the normal predictions of quantum mechanics. So if I'm right about this, then it means that I actually know what quantum mechanics is. I have a completely physicalist description of quantum mechanics. Like I know what the universe, all these questions about like what actually exists. Does the wave function exist? Does the wave function only description of subjective knowledge? What's going to happen if you're doing a Schrodinger cat experiment on yourself? All those questions are questions that I can answer now.
Okay. And what does that look like?
So the way it looks like is basically that, well, in quantum mechanics we have different observables, and usually you cannot measure different observables simultaneously unless they are like corresponding commuting operators. So what happens here is like you kind of imagine that the universe, like the universe has some Hilbert space and it has some wave function which is like some state or some pure or mixed, doesn't matter, state on this Hilbert space. And then like you have all the observables, and the universe is measuring all of them actually. The universe is measuring all of them, and like the probability distribution over outcomes of each observable separately is just given by the Born rule. But the joint distribution, and here it's a funny thing, the joint distribution, we just have complete Nike uncertainty about what the correlations are. So we're just imposing the Born rule for every observable separately, but we're not imposing anything at all about their correlations. And I'm claiming that this thing produces the usual predictions of quantum mechanics. And one way to think about it is when you're doing the bridge transform, and then you're kind of doing this information decision theory on what results, you're looking at the worst case. And the worst case is when the minimal number of computations is running because of this monotonicity principle. So, in some sense, what happens with quantum mechanics is the relevant or kind of the decision relevant joint distribution over all observables is the joint distribution which corresponds to making the minimal number of computation. It's like as if the universe is really lazy and it wants to run as little computations as possible while having the correct marginal distributions, and that's what results. So the interesting thing about it is you don't have any. So there's no multiverse here. Like there's like every observable gets a particular value. That just you have some randomness, but it's just normal randomness. It's not like some weird multiverse thing. There's just only one universe. you can get some weird things if you're doing some weird experiment on yourself where you're becoming a Schrodinger cat and like doing some weird stuff like that. You can get a situation where multiple copies of you exist. But if you're not doing anything like that, then there's just one branch, one copy of everything. And yeah, that's what it looks like.
Sure. And does that end up so in quantum mechanics there's this theoretical result that says like as long as experiments have single outcomes and as long as they're probabilistic in the way quantum mechanics says they are, you can't have like what's called local realism, which is like some sort of underlying true fact of the matter about what's going on that also basically obeys the laws of locality, that also doesn't like internally do some like faster than light or backwards in time signaling. And like there are various parts of that you can give up. You can say like, okay, well, it's just fine to not be local, or you can say like experiments have multiple results, or there's no underlying state or something. Which it sounds like in this interpretation you're like giving up locality. Is that right?
Yeah, it's definitely not local in the sense that local is defined for the purpose of this theory is it's absolutely not local. But what's good about it is that it's still, as far as I can tell, it's still completely Lorentz invariant. So in this sense, it's different from, there's things like the Berle-Baum interpretation, which also gives up on locality, but then it also loses Lorentz invariance, which is really bad in my.
And Lorentz invariance is basically like, do you play well with special relativity, right?
Yeah, and here you don't have any problem like that.
Okay, that's interesting. Well, I look forward to reading more about that in future. Are there any other follow-ups to this work that you're excited by?
Yeah, well, there are a lot of interesting things that I kind of want to do with this work, like proving physicalist regret bounds or some kind in more detail. Or like one thing that I kind of want to do is have some kind of an enhanced Oman agreement theory for physicalists. Because what happens is that, with the usual Oman agreement theorem, you have the problem that it kind of assumes that all agents have the same prior, but if your agents are Cartesian, then in some sense they don't have the same prior. Because like each agent has a prior which is defined from its own subjective point of view. And this can cause failures of agreement. And in particular, I claim that like Paul Christiana has this thing which is called the Solomon of prior is malign, which can be summarized as like if your AI is doing something like Solomon of prior, then it can reach the conclusion that the world is actually a simulation by some other intelligent agents. And those other intelligent agents can actually cause your AI to do bad things or like cause your AI to do things that they want it to do. And this scenario is a kind of failure of Oman agreement in the sense that the AI sees the same evidence as you, just from a different vantage point. But from the AI vantage point, it reaches the conclusion that it's in a simulation, even though from your vantage point, you should not have reached the conclusion that it's in a simulation. And I kind of conjecture that in infra-Bayesian physicalism, you can prove some kind of an Allman agreement type theorem that like different agents inhabiting the same universe have kind of this Allman agreement because they don't privilege their subjective points of view anymore. And therefore, this kind of failures cannot happen.
Okay, that's interesting. So, I guess another question is apart from follow ups, are there any complements to this line of research that you're excited by? So, things other people are doing that work really nicely with infra-Bayesianism or infra-Bayesian physicalism?
Well, I'm not super aware of things that people are actively doing and it obviously work very nicely. I mean, just a couple of days ago, I read this post by Abram Damsky in which he's talking about his thoughts about elucidating latent knowledge, which is like this problem of we have an AI and we're trying to make the AI tell us everything that it knows about the world and kind of tell us honestly. And kind of a sub-problem that he discusses there is this issue where if you have different agents, they have different kind of subjective vantage point. So what does it even mean for them to talk about some shared truth? Like what does it mean for the AI to tell us honest answers if the AI's truth is formulated in some completely different domain, which is like its own subjective point of view? And here, for example, Abram even mentions computationalism as a way to solve it. And the nice thing here is that infra-Bayesianism actually formalizes computationalism and gives you this kind of shared domain, which is like which programs are running and what values do they take, which is kind of a shared domain of truth between different agents that you can use to kind of solve this kind of philosophical issue.
Okay, interesting. I guess I'd like to talk a little bit about you as a researcher. So, what does it look like for you to do research?
Well, I mean, my research is a kind of very theoretical, mathematical type of research. There are like several components to the process. One component is how do we translate the problems or the kind of philosophical or informal problems that we care about into mathematics. And then there's like, how do we solve the mathematical problems that result? And those two processes, they are kind of living in some kind of a closed loop with each other because if I come up with some mathematical model and then I analyze it and it leads to conclusions which don't make sense in terms of the way I want to apply this mathematical model, then I know that I need to go back and revise my assumptions. And on the other hand, sometimes I'm playing with the math and something just comes out of playing with the math, which can tell me that, maybe maybe it's a good idea to make such and such assumption, or like think about this informal concept in terms of this mathematical construct. So those are two kind of coupled processes, and yeah, what's guiding my thoughts is, I mean, there's a goal. Like the goal is kind of causing AI not to kill everyone, right? And then there's like sub goals that we can derive from this goal, which are like different problems that we want to understand better, like different confusions that we have that might have implications on our ability to think about AI safety, or just directly thinking about what kind of AI designs can have what kind of safety guarantees. And then, like, those kind of informal sub problems, I'm then trying to come up with formal mathematical models for them. And my process here is always kind of try to start with the most simplistic model that's not meaningless. Like, if I have some informal problem and I'm trying to think of some kind of a model for it, I'm thinking, let's make the strongest possible simplifying assumptions that I can imagine, under which I can do something, anything, as long as it doesn't degenerate into something completely trivial. Like if I can make a bunch of simplifying assumptions and under those assumptions get a mathematical model in which I can prove something not trivial, like I can prove something which actually requires work to prove it and not doesn't just follow directly from the definitions the way I define them, then it makes me feel like I'm making some progress. And once I have this kind of foothold, I can then go back and say, okay, so in this simplified toy world, we solved the problem. Now let's go back and see how can we remove some of those simplifying assumptions. And then hopefully step by step, you can kind of climb towards a solution which starts looking realistic. And of course, it looks like many convergent lines of research. Like there are many problems, and eventually you need to solve all of them. And eventually they're all kind of coupled and interacting with each other. But like with each of them, you make a bunch of simplifying assumptions. So you manage to kind of divided from the other problems. So there's some kind of divide and conquer going on. But then as you start removing your simplifying assumptions, you also need to start merging those lines of research together until hopefully somewhere in the end we'll get a grand big theory of AI and AI alignment, and we'll be able to just solve everything we need.
Nice. Let's hope. So I'm about to wrap up, but before I do that, I want to ask, is there anything that you think I should have asked, but I didn't?
I mean, one thing we haven't really talked about is the whole malign prior thing and what are the implications of physicalism in this context.
Sure. So what is the malign priors thing?
So the malign prior is a problem articulated by Paul Cristiano, and recently there was also this post by Mark Sue, which gave some explanation, elaboration, and summarizing of previous posts about that. And this problem is interesting because it seems really, really weird and kind of, you know, it kind of triggers the absurdity heuristic really hard. But the more you think about it, the more convincing it seems, at least for me. So the gist of what is going on is the following: that in usual Cartesian approaches, we have those bridge rules. And those bridge rules, they produce very, very complex hypotheses. And this means that simulation hypotheses can sometimes start looking a lot more attractive than non-simulation hypotheses. Why? Because, like, imagine that there is some universe with some relatively simple laws of physics that contains some kind of intelligent agents. And those intelligent agents, they want to take over our universe. So what they might do in this case is, and they're like, no, that in our universe, we're building this AI, which is gonna be really powerful. So what they might do is run a simulation of our AI seeing things in our universe. And they run it in a way such that it's encoded in the most simple degrees of freedom that they can manage to control. Like, they're running the simulation, and the output of the simulation is written into their analog of electron spins or whatever, something that's fairly easy to describe in terms of basic physics, as opposed to things like pixels on a camera, which are very complex to describe. If they're doing this thing, then REI can say, okay, what should I believe? Am I in this like normal universe with the normal Earth, but with this extremely complex bridge rules, which look completely contrived and arbitrary, and like, give me a huge, huge penalty to my hypothesis? Or maybe the correct thing is this simulation hypothesis with this much simpler bridge rules that come off from reading the output of the simulation of those electron spins or whatever. That other thing now seems much, much more plausible. And what happens here is that the attackers,
Sorry, wait. Why does it seem more plausible? The other thing?
because the complexity is much lower. So we don't have the complex bridge rules. We have some much simpler bridge rules. So the complexity can be lower.
And you're penalizing complex hypotheses.
Yeah, and that can be like super substantial. Like maybe you shaved off 100 bits of your hypothesis complexity. So now you have like a factor of 2 to the 100 in the relative likelihood. So you can end up in a situation where your AI is not just considered as plausible, but practically completely convinced that it's in a simulation. Like the simulation hypothesis is just overwhelmingly likely from its perspective. And what's happening here is that the attackers are exploiting that the AI is in a very, very special position in the universe. And the AI is thinking like, I found myself, according to the normal hypothesis, is just a completely random fact that I'm this agent in this place in the universe, as opposed to a different agent, or as opposed to just random clump of dust somewhere in outer space. It's just a completely random fact that I need to hard code into my hypothesis that I'm this agent. Whereas from the perspective of the other hypothesis, there is a completely logical mechanistic explanation of why I'm seeing this. I'm seeing this because this is what the attackers want to attack.
Okay. And why is it why do they count as attackers? Like why is this bad? If they're simulating the same things.
Well, the bad thing comes because they can now, once they convinced our AI that it's in a simulation, they can alter its predictions in arbitrary ways. Like when AI is asking itself, okay, what do I expect to see in the future? The simulators have complete control of that. Like the limitation they face is that if they make a prediction which is not true in our universe, then once the AI sees that it's not true, the simulation hypothesis has been falsified. But by this point, it might be too late. They can carefully engineer this future prediction in such a way that will cause the AI to do something irreversible. And from this point, it already doesn't matter that the prediction will be falsified. In their simulation, the AI should replace itself with a different AI that has different source code. And if it does not do that, then something completely horrible happens in the simulation. If it does do that, then something absolutely amazing and wonderful happens. And the AI is just going to do this. And once the AI done this, then it's already too late. The fact that the future reveals that the amazing, wonderful thing that was supposed to happen didn't actually happen doesn't save us anymore because the AI already replaced itself by some different AI, which is just doing whatever the attackers wanted to do.
Yeah, there are constructions of this where I think the simulating AI says, okay, I this AI it has to follow this exact certain policy. It's got to do all these things. If it ever deviates from that, incredibly terrible things are going to happen, and you can just predict whatever you want because if it's so terrible, you can convince the AI you're attacking to just never deviate, so it never finds out. Um, Seems like a different spin on the same thing.
Yeah, I mean, like in the reinforcement learning, you have the problem indeed gets worse because, like you said, like counterfactual predictions can never be falsified. If you're trying to kind of avoid this by having your AI only do forecasting or something, like you're trying to, do some kind of an iterated distillation and amplification thing in which your AI is not actually doing reinforcement learning, but kind of only doing predictions, then you're still gonna lose because of this other problem that you're just the simulators are just gonna make it up with whatever prediction is going to cause irreversible consequences in our universe that benefit them.
Okay. And basically, the upshot is this is why we should be worried about these bridge rule formalisms, and this is why we should prefer something like Infra-Bayesian Physicalism, I guess.
Yes, with the caveat that maybe physicalism can also kind of arise by itself in some sense. And this is something that we're still a little confused about. So when we wrote the article, what we actually wrote there is that, like one question you can ask is, okay, maybe if your agent is some kind of an AXI or Cartesian agent, maybe you can just discover physicalism as one of the hypotheses in its prior, and from there on, it will just behave as like as a physicalist. And what happens is if you're just trying to do this kind of very straightforwardly, you run into the problem where, like, if you're just trying to do this with AXI, then you run into the problem that in order to define physicalism, the agent needs to use its own source code, but AXI has infinitely long source code because it's incomputable. So this hypothesis is going to have like infinitely big description complexity. But actually, if instead of just AXI, you're thinking of kind of Turing reinforcement learning thing, then you can kind of work around this because like the computer that you're kind of working on, it might be able to run some short versions of your source code. Like, if you're like AXI, this is just like a toy example, but like if you're AXI, but your computer has a halting oracle, then like your computer can implement AXI as a short program, and you can kind of use that to define a physicalist hypothesis. So maybe some types of Cartesian agents can, well, if they're doing like Turing reinforcement learning or whatever, but they're still not doing the full physicalism thing, then maybe they can kind of discover physicalism on their own. and that would kind of ameliorate some of the problems. But it would still, I mean, you would still have some advantages if you just start out physicalist. And even if it doesn't actually matter, in practice, you don't actually need to explicitly make your agents physicalism, then it still seems really important if you want to analyze and like understand what's actually going to happen, because this kind of shows you that like the actual hypothesis your agent ends up with is something very different from what you could naively expect. So you really need to take this into account when you're doing any kind of analysis.
Okay, so that was the last question I need to ask. So I guess we're done now. So just while we're wrapping up, if people listen to this interview and they want to learn more, they want to follow you and your work, how should they do that?
So the easiest thing is just to follow me on Alignment Forum. So I post all of my work there, more or less. And if someone wants to ask me some concrete questions, or like thinking of some collaboration or something, then I'm always happy to discuss AI alignment things. So they are just welcome to email me at vanessa.kosoy@intelligence.org.
Great. Well, thanks for appearing on the show, and to the listeners, I hope you'll join us again.
Thank you for having me.
This episode is edited by Jack Garrett. The opening and closing themes are also by Jack Garrett. The financial costs of making this episode are covered by a grant from the Long-Term Future Fund. To read a transcript of this episode, or to learn how to support the podcast, you can visit axerp.net. Finally, if you have any feedback about this podcast, you can email me at feedback@axerp.net.